Hello everyone, I will be doing problem 3.10. So this problem asks for for part A to find the potential in the region above the plane where we have a uniform line charge lambda on an infinite straight wire that's a distance d above this ground conducting plane on the xy plane. So we know from this past section that we can use this method of images to find our solution to the potential, and that comes from the uniqueness theorem, which we know gives us a unique solution to Laplace's equation. So we can create an image of something very similar to what we already have, but it can make our problem a lot easier. So we can have we can still have this lambda infinite line charge distribution, a distance d above the x-axis, but now we can create this this negative line charge, a distance d below the x-axis, and we can find the potential from this problem, and it will give us the same solution to this problem because there's only one solution. So we can use Gauss's law, where we know that E dot dA is equal to the charge enclosed over epsilon naught, and we can find the we can find it using Gauss's law by using a Gaussian cylinder on this infinite line charge. So we know we can take this electric field out of the equation, so you're just left with an E dot dA, and the charge enclosed is this uniform line charge times a distance L for your Gaussian cylinder over epsilon naught. And we can find the surface area of this Gaussian cylinder to be 2 pi s times L, where this S is coming from cylindrical coordinates, where it's the distance coming radially outward from this cylinder. And when we cancel these L's, we can find that the electric field due to this infinite line charge to be lambda over 2 pi s, or 2 pi epsilon naught times s. And since we have 2, we can use the same method to get a positive electric field to be lambda over 2 pi epsilon naught s plus, and E minus to be negative lambda over 2 pi epsilon naught s minus. Now, what are s plus and s minus in Cartesian? So we can make a 2D image of what we have here to be the z-axis here, and the y-axis here, and we have this lambda, positive lambda here, and this negative lambda here, with the distances d from the origin. And when we are trying to find an arbitrary point yz on the yz plane, because this x, because both of these are parallel to the x-axis, we know that this is going to be s minus, and this is going to be s plus. So if we find this distance, s minus z minus d, then we can create, or we can find what s plus to be y squared plus z minus d squared, quantity squared rather, and s minus to be y squared plus z plus d quantity squared. So, and both of these are going to be in the s plus and s minus directions, because it's going to be radially outward. So we can find this potential to be v plus to be negative E dot dl, where our dl is ds s hat. So this would be negative lambda 2 pi epsilon naught. And from here we can use this reference point of distance d from the origin to s. In this case, we're finding the positive one, so we can use s plus. We're going to make dummy variables here. So we're going to get negative lambda over 2 pi epsilon naught times natural log of s plus minus natural log of d. More compactly, this can be written as lambda, well, we can put this negative inside of this parentheses, and more compactly we can write it as natural log of d over s plus. Similarly, we can find the negative potential, just writing all of these steps out again, except this time we're going to be using a positive, or a negative lambda, which means these negatives are going to cancel. Similarly, we're going to use the same bounds, but instead of s plus, we're going to use s minus. Giving us lambda 2 pi epsilon naught natural log of s minus, just write parentheses here, s minus minus natural log of d. So more compactly, we can write it as lambda 2 pi epsilon naught natural log of s minus over d. So, since we found the two potentials from both of these line charges via superposition, we can find the total potential by just adding these together. And this gives us lambda 2 pi epsilon naught natural log of d over s plus natural log of s minus over d. And using our natural log rules, we can find that this is lambda 2 pi epsilon naught s minus over s plus, since these d's will cancel out. And we can write this using our Cartesian formula up here for the s plus and s minus, and we find that it will be equal to lambda over 2 pi epsilon naught, natural log here, times the natural log of y squared plus z minus d squared, all over the square root. And similarly, this is a plus here, y squared plus z minus d quantity squared, in the square root. And using our natural log rules, since these are both to the 1/2 root, this can come out of the natural log, giving us a potential of lambda over 4 pi, because this 1/2 is going to come out, 1 over 4 pi epsilon naught times the natural log of y squared plus z plus d, quantity squared, over y squared plus z minus d, quantity squared. And that gives us our potential. So part B asks to find the charge density sigma induced on the conducting plane. So we know from the equation, so sigma is equal to negative epsilon naught dv dn, dv dn, where this n is this normal vector. Since we're finding it for the conducting plane, this normal vector will always be pointing in the z direction. So we find that this is the equal to negative epsilon naught times the derivative with respect to z. And since this conducting plane is at the x and y plane, we make this equal to 0 because it's on the surface. And we're going to be taking a derivative with respect to z, so it might be a little bit easier to explicitly write this as lambda 4 pi epsilon naught times the natural log of y squared plus z plus d squared minus the natural log of y squared plus z minus d squared. So we could take this derivative at the surface, making z is equal to 0. So this lambda over 4 pi epsilon naught will come out. And then we're going to take the derivative of this natural log, giving us 1 over y squared plus z plus d squared. We're going to do the chain rule, multiplying, or giving us a derivative of 2 times z plus d. Similarly, for this next natural log, we're going to get 1 over y squared plus z minus d quantity squared times 2 z minus d, using the same derivative rules we just applied. And that's all when z is equal to 0. So we find that this lambda 4 pi epsilon naught is going to stay in the front, giving us this z is going to go to 0, this z is going to go to 0, this z is going to go to 0, this z is going to go to 0. So we get 2d over y squared plus d squared minus negative 2d over y squared plus d squared. And this gives us lambda 4 pi epsilon naught times 4d y squared plus d squared. These 4's are going to cancel out, and we're just going to be left with lambda times d over 4 pi epsilon naught times y squared plus d squared. Oh, a little bit out of the screen here. And finally, we can apply this back and get our surface charge to be negative epsilon naught times this expression, lambda d over 4 pi epsilon naught y squared plus d squared. These epsilon naughts are going to cancel, giving us negative lambda over d. This 4 should not be here. This 4 canceled out with the other one, giving us negative lambda times d over pi times y squared plus d squared. Giving us our answer for B. Thank you.